that leaves an impression, leaves its mark on society and, of course, the economy. And that stayed true, regardless of where I've lived, where I've traveled to, all the different types of weather that I've experienced over the years. I'm constantly amazed, I'm constantly in awe at what the atmosphere can do. I'm sometimes very terrified at what the atmosphere can do and how the Earth system responds. And as our observing systems, our observational networks, our numerical models have gotten better and better over time and continue to advance, we continue to learn more and more about extreme weather, about high impact weather events and the range of impacts they have and how it feeds back on the Earth system. But these advances also open up a new can of worms. They open up a whole new set of questions around the dynamics, the predictability, the projections of high impact weather. So it's this grand challenge, if you will, these open science questions around weather and climate extremes that really motivate me to have gone into this space to begin with as a student way back in the day and to continue working into this space into my career. So using this motivation, throughout my career so far, I've developed a research experience for sure, dare I say, maybe expertise, centered around high-resolution modeling of extreme weather, both from regional perspectives using models like WRF and then transitioning to global perspectives using MPAS. And I think that these two quotes do a really great job summing up my general research philosophy thus far. We, of course, have the famous quote by George Box, "All models are wrong, but some are useful," and this quote by Pablo Picasso, "Learn the rules like a pro so you can break them like an artist." And that's really what I like to do. I like to push models sometimes to their breaking points. I like to isolate systems, isolate processes, really pick things apart to try to help us understand as best as possible what's going on and how processes like climate change or latent heating, for example, can impact extreme weather phenomena. So it probably goes without saying, based on the title of the talk, that my tool of choice for carrying out these types of experiments is MPAS, which I'm sure needs no introduction to this audience. But the reasons for why I got into using MPAS and have stuck with it really tie back to those open science questions revolving around that intersection of weather and climate. So for instance, a lot of our conversations when we talk about climate change, when we talk about the need for predictability improvements, it's usually centered around high impact weather. How can we improve forecasts of high impact weather and their impacts? And how might these events look like in the future? What might those look like as we move forward in time? And on the climate side, while the resolution of our GCMs has gotten better and better over time, and with the past few model generations, we still don't have a huge number of model simulations at sufficient resolutions to really get what we want. We want to look at tropical cyclones, mesoscale convective systems, and so on. So we still have some way to go there. And regional climate modeling helps in a lot of ways. We can employ techniques like the pseudo-global warming method. We can do regional dynamical downscaling, and that really does help us get at much finer scales, but introduces another set of limitations in that we're constraining those lateral boundaries, and that can somehow prevent the whole picture from being realized. And then from a predictability perspective, our predictability experiments require whatever event that we're interested in, require those to be adequately simulated in a control simulation, which I'm sure many of us can attest by experience that that's not always the easiest thing to do. So our idea here with a couple of the data sets that I will present is to try to address some of these limitations and really start looking at that bridge between weather and climate modeling. And so the benefit here of using MPAS is the fact that it is global, so we're not constraining our lateral boundaries, and the fact that it's atmosphere only, which means that we can prescribe sea surface temperatures at higher resolutions. And that can be seen as a benefit and a limitation depending on your modeling perspective. But for our needs and our purposes, we wanted to make sure that we didn't have biases in ocean representation, and we wanted to help constrain the model as we integrate over these long durations. So for the two experiments I'll talk about today, in particular, another motivation was just curiosity. What happens if we run MPAS for 5 years, for 10 years, for 30 years? How does the model perform? What does the model climate look like? So as I said, I'll talk about two of these, quote, climate mode MPAS experiments today. set the stage for James and Gabrielle, who are here in the front for their happy hour seminar tomorrow, using these data sets and looking specifically at some high impact weather. So the first one here is from my PhD work at NC State University using MPAS and what we called a, quote, daisy chain technique to produce present day and future simulations. The motivation for why we did this experiment in the first place was really to study the extratropical transition of tropical cyclones. But as I'll mention here towards the end of this part, the data set has already been used for a couple different phenomena, and I would love for it to be used for a wider audience. Okay. So for these simulations, we used version 5.1 of MPAS and with a variable resolution mesh that has 15-kilometer grid spacing over the whole Northern Hemisphere, and that expands out to 60 kilometers elsewhere. For initial conditions, we used the ERA interim and updated sea surface temperatures and sea ice fields every day using the operational sea surface temperature and ice analysis dataset. The OSTIA dataset provides super fine resolution for those fields. Our physics choices are listed here. We have WSM6 for microphysics, YSU boundary layer, TITCA for convection, and CAM for long and shortwave radiation. We chose TITCA in particular because its inclusion of convective momentum transport, and again, because we were motivated by looking at tropical cyclones and extratropical transition, we wanted to make sure that we had that process included. And then we also did some preliminary testing at 60 kilometers to further refine those choices. So we picked 10 years to simulate for this project, and we chose these years to sample varying phases of ENSO based on the MEI and ONI indices over the TC season. Our simulations ran for 14 and a half months, so we started on March 1st of the first year and then ran through mid-May of the second year. And we chose this time span to, of course, simulate the core TC season, so June to November. We also wanted to make sure to get a couple shoulder months on either side in case of potential seasonality shifts in our future simulation. And then we figured while we're at it, we're using the people time, we're using the computing resources. Let's go ahead and simulate a full winter season so that this data set could be applicable for other applications. So we have our selected years, which are listed here. You're probably thinking, Allison, why can't you put things in chronological order? There is a method to that madness. Because we don't have 10 consecutive years, we wanted to make sure that we conducted our simulations in such a way that minimizes spin up for each simulation year, but also minimizes the shock to the system as we move from one year to the next. So instead of chronologically, we organized our simulation years from the strongest La Nina year, being 2010, to the strongest El Nino year of 1997. And this is where we employed that, quote, daisy chain simulation technique. So the first thing that we did, we ran a full 14 and a half month simulation for a neutral ENSO year of 2013. This was a spin-up simulation. It's not used in any analysis. And then we took the output towards the end of the simulation, so March 1st, 2014, and we used that to initialize our first, quote, production year of 2010 there. So we're using that output from the MPAS simulation itself, from that restart file, to start this new simulation. We swap out those sea surface temperatures that are representative of 2010, and then we give the model about a month of spin-up time to adapt to that change. And then we continued with this method where we used March 1st, 2011 to initialize the next year, 1988, and so on and so forth down the line. For post-processing, we interpolated temperature, wind, height, all of our 3D fields to select pressure levels, and then interpolated all of our fields to a 0.15 degree by 0.15 degree lat-long grid. We, of course, had storage limitations. We were only allowed to save select variables, and we only saved data for the Northern Hemisphere. But we did save monthly restart files throughout the whole 10-year period. So if ourselves or any other group wanted to go back, run a particular season, run a particular case of interest, output at finer temporal resolution, output more variables, that is possible to do so. And then to examine the effects of climate change for our future 10-year period, we simulated those same 10 years, but with altered thermodynamics. And our method for this, at least for that first spin-up year of a neutral 2013, was along the lines of PGW, along the lines of pseudo-global warming, where we calculate those monthly average temperature changes from a subset of GCMs and then use those to alter our initial conditions and sea surface temperatures. We did use CMIP 5, and we followed RCP 8.5, so our high emission scenario here. And we took our 100-year temperature changes by subtracting the 1980 to 1990 average temperature from the 2080 to 2099 average temperature. And we get a pattern that looks something like this. As an example, I believe this is for the month of March. And then we take these temperature deltas, and as I said, we tack those on to our initial conditions at all pressure levels, at soil levels, and onto our sea surface temperatures that are updated daily. And I'll talk about a little bit more about that in a second. So with these warmed initial conditions and sea surface temperatures, we can essentially produce a simulation for 2113, 2110, and what have you. So as I mentioned, we handled our sea surface temperatures in a very similar way that we handled our initial conditions. We calculate those 100-year temperature deltas from GCMs, an example shown here at the top, again for the month of March, and tack those changes onto our existing sea surface temperatures from the ASTIA dataset. So that's what you're looking at here. On the left, we have an animation of current sea surface temperatures from March 2013 through May 2014. And on the right, we have our future sea surface temperatures over that same period. So handling the sea surface temperatures this way allows us to preserve those high resolution gradients, those high resolution sea surface temperature features, not only in the historical and the present day simulation, but also maintaining those features in the future. Dealing with sea ice, though, wasn't as simple. We couldn't just calculate a sea ice delta and tack that on in the same way, so we got a little creative. So instead, we used the monthly average sea ice fields from our CMIP 5 ensemble mean for the historical and the RCP 8.5 emission scenario, and then created these pseudo-daily sea ice fields by doing a 31-day running average. So this is what those fields look like. We have current on the left and future on the right. And I'll let this play through a little bit, again, starting in March and running through the next May. And we can see that the sea ice basically all but disappears in the summer and fall in their respective hemispheres under this high emission scenario, which is super depressing if you think too much about it but scientifically, it was a good thing to do. So what we essentially did was just replace the sea ice in the ASTIA data set with the fields that you're looking at here. And we used the same sea ice fields for all of our 10 simulation years, rather than swapping it out like we did for sea surface temperatures. So getting into model evaluation. The biggest questions that we had in mind when designing and evaluating the simulation were, of course, is it going to work? Can we do this daisy chain technique and have a 10-year model climatology that looks something like we expect it to based on reanalysis? Second, with the climate change, again, does this work? Can we do our climate change simulations in a similar manner? And can we replicate some key warming signatures that we expect to see based on GCMs? And then, of course, because our original motivation was to study extropically transitioning tropical cyclones, we wanted to see, can MPAS designed this way present and replicate a TC climatology that looks like what we wanted it to. So in the interest of time for evaluating the present day mean climate, I'll just focus on wintertime patterns of sea level pressure variance as a metric for storm track activity, and look at annual patterns of tropical precipitation. And then for our climate change evaluation, we'll look at plan views of near surface temperature and temperature cross sections. And then in terms of TC climatology, we'll look at track density and distributions of storm intensity. So we have our two primary mid-latitude storm tracks in the North Pacific and the North Atlantic, at least in the Northern Hemisphere. And we know how important the extratropical cyclones that occur in these storm tracks are for our climate system as well as our day-to-day weather. And of course, their connection back to high impact weather. So it was super important for us to make sure that these MPAS simulations credibly represented these features. And as suggested by Cheng and Fu in 2003, can use mean fields as a proxy for storm track activity. So here we use sea level pressure variance as a metric for wintertime, so December, January, February. At the top here is the ERA interim climatology. It's really hard not to say ERA 5. I'm so used to that now. But the ERA interim climatology, and at the bottom here is our MPAS climatology. They are both over 10-year periods, so our MPAS climatology being, of course, over our 10 simulation years. But we did the same for ERA interim to help most apples-to-apples comparison as possible. So this ERA interim is, again, a 10-year climatology over just those same simulation years. And we do see both of our North Pacific and North Atlantic storm tracks clearly present in the model, which is great. There are, of course, a couple slight differences to point out. For one, the North Pacific storm track appears maybe slightly more zonally oriented in MPAS. And the storm activity in the Northeast Atlantic and over the Central North America is slightly underestimated. But we don't expect them to match perfectly. And overall, we have a spatial pattern correlation coefficient greater than 0.95. So MPAS does do a nice job with these features. Another large-scale mean field to check is the representation of tropical precipitation, which is shown here for TRIM in the top panel and MPAS in the bottom panel. And I will note that for TRIM here, we did just use the full 19-year climatology. So some things to note, the ITCZ, especially in the Central Pacific, is pretty well represented, as is the mid-latitude storm track in the Atlantic. There is, however, a large overproduction of precipitation in the Western Pacific, which could at least be in part due to some overactive tropical cyclones in that region, which I'll show here in a bit. Also, the precipitation maximum in the equatorial Atlantic is shifted a bit westward in the model. We did look a little bit into the African easterly jet and also noted a westward shift in the African easterly jet, so that could be at least partially responsible for this signature as well. But again, our pattern correlation around 0.95, very highly correlated, so we were pretty pleased with how MPAS represented these patterns. In terms of climate change signals, one of the things we were looking for is Arctic amplification. So the notion that the Arctic region is warming at a much faster rate compared to the rest of the globe. And so to look for that, we looked here at near surface temperature, so 2-meter temperature. This is the difference in annual 2-meter temperature calculated as future minus current. So the reds and oranges here indicate warming in our future runs, and the blue colors here indicate cooling, which I don't believe we see any in these particular fields. And on the top here is our difference field for the CMIP-5 ensemble mean that we use to calculate our temperature deltas, and the bottom is for MPAS over our 10 simulation years. And the good news is that MPAS is capturing that Arctic amplification effect, albeit to somewhat of a stronger degree. And we're also getting some warming maxima in roughly the same areas, like northeast of Scandinavia, for example. And MPAS did show a stronger warming maximum here over North America, which doesn't appear as prominently in the GCM ensemble mean. So perhaps MPAS is able to pick up on some enhanced topographic effects due to that increase in resolution that aren't necessarily resolved in the GCMs. The other warming signature we wanted to make sure that MPAS captured is the warming maximum in the tropical upper troposphere, which we looked for here in a cross-section of zonally averaged annual temperature, again, taken as future minus current. We have the CMIP-5 ensemble mean on the left and MPAS on the right. And yes, our tropical upper tropospheric warming maximum is evident in our simulations, and we see some other features also compare well between the two. For one, we have this area of cooling in the upper troposphere in the high latitudes that appears both in the GCM ensemble and MPAS, albeit that magnitude of cooling is a bit stronger in the CMIP ensemble mean. That region of Arctic warming also appears in both images, although it is a bit shallower in MPAS compared to the GCM ensemble. So overall, though, we're pretty confident in the simulation technique, how the future simulation performs, regarding these signatures. So to track tropical cyclones in our simulations, we use Tempest Extremes from Ulrich and Zarzicki 2017. It initially detects candidate centers as minima and sea level pressure, and then retains candidate centers based on a variety of different criteria, like requiring a closed sea level pressure contour of some strength within some distance of the center, requiring the presence of a warm core, so on and so forth. And then those candidate centers are stitched together to form TC tracks based on another set of criteria. So there are a lot of tunable parameters associated with tempest extremes. We spent some time doing some manual analyses and testing these out to see which ones worked best for our model runs. I just have a couple listed here for reference, but there are, of course, several others. So to give you an idea of what these tracks look like, here are all the TC tracks from May through December in 2010 from the present day simulation. And as you can see, we are getting TC activity in all northern hemispheric basins in just about the right places. But we look at the full 10-year TC density, however, our climatology, we see a slightly different story, at least regionally speaking. So here we have that track density. It's calculated as the number of storms per 1 degree by 1 degree box over the 10 years. We have IB tracks at the top, again, just over that 10-year period, just like we did for Era 5. And then MPAS 10-year climatology here at the bottom. So in general, we do again have MPAS TC activity that's reasonably well. Here's that overproduction in Western North Pacific TCs I mentioned earlier that could be correlating with that enhanced tropical precipitation. But the main discrepancy is, of course, the lack of storms in the eastern North Atlantic. We did look at a couple different metrics at the time and did see a positive bias in vertical wind shear here for August and September that could be a culprit to look more into. At the time, our hypothesis was that our mesh configuration could be causing part of this issue. The fact that we have that 15 to 60 kilometer transition zone starting just north of the equator, and perhaps that was causing some feedbacks and some discrepancies there. But as James will show tomorrow during the happy hour seminar, this is more of a systematic bias for these long-term MPAS simulations and definitely requires more investigation. And then looking more into simulated TC strength, we have a scatter plot here of maximum 10-meter wind speed on the x-axis versus minimum sea level pressure on the y-axis. Our black dots here represent IB track storms, and the gray dots represent the storms simulated by MPAS. And then each distribution includes a second-order polynomial line of best fit. Vertical lines here are the Saphir-Simpson threshold categories, intensity threshold categories based on maximum wind speed. Horizontal lines here are intensity thresholds, as in Roberts et al. 2017, based on minimum sea level pressure. And a commonality among many modeling studies is an underestimation of TC intensity, especially in terms of wind speed. So with our simulations in particular, over these 10 years, we did see a couple of Category 4 storms based on maximum 10-meter winds, which is decently impressive. We weren't expecting to get Cat 5 winds at 15 kilometers, although we held out hope for that. But if we do consider intensity based on minimum sea level pressure, we are able to simulate some Category 5 storms, and really storms across the full intensity spectrum. So, as I showed here for part 1, this first experiment, our future MPAS run did reproduce those two key warming signatures of Arctic amplification and that tropical upper-tropospheric warming maximum, which is pretty remarkable, considering all we did was warm the lower boundary and crank up CO2. And we got some signatures that look very similar to what the GCMs produce. MPAS was also able to realistically represent some large-scale mean features like mid-latitude storm tracks, jets, which I didn't have here, but they are in the paper, and RTC climatology and tropical precipitation, albeit with some noticeable biases there, especially for the TC climatology. And as I mentioned, we've already been using this data set for a few different things. So far, as I mentioned, we've used this for extratropical transition of tropical cyclones in Michaelis and Lachman 2019 and 2020. Lachman et al. 2021 looked at persistent anomalies and the impact of climate change on persistent anomalies. And Turnau et al. 2022 looked at climate change impacts on Eastern European heat waves. And then, of course, we have some ongoing projects looking at extreme precipitation, which Gabrielle will talk about tomorrow, We're looking at atmospheric rivers, and then continuing that extratropical transition work and looking at more of the downstream impacts. So if y'all have any thoughts on how you might want to use this data set, I'm happy to chat later. I'm also happy to pause here and take questions about this particular part if we want before I move in. Can go with the flow. Or we can wait till the end, it doesn't matter. Okay, we'll roll on. So the second data set I'll talk about is a more recent effort. We produced a 30-year, quote, AMIP-style nature run simulation with MPAS. And this was a huge modeling effort with support of a whole collaboration team here, help with the initial modeling design with some of the post-simulation analyses, and some of which I'll showcase here. So for these simulations, we used MPAS version 7.0, and we used a 15-kilometer quasi-uniform mesh. For initial conditions, we use the ERA 5 reanalysis, and just like the other experiment, we do prescribe sea surface temperatures and update them daily, and we again use that OSTIA superfine resolution data set. I will note that the information from those initial conditions is forgotten by the model fairly quickly, since we are just running continuously all the way through 30 years. We initialized in September of 1989, again ran continuously for 30 years. So we have a full analysis period spanning 30 water years from October 1st, 1989 through September 30th, 2019. A few of our physics choices are listed here. I mainly wanted to point out that we're using the scale-aware version of the new TITCA scheme, thinking that if we want to do some additional experiments down the line at finer scales, then we're able to keep that consistency and we don't have to worry about swapping out that CP scheme later. So a couple stats for computing time and storage in case you're interested. I'm sure this will all seem like a drop in the bucket for those of you working on the 3-kilometer long-term runs, but at the time, these kind of storage blew my mind a little bit. The 15-year runs that I just presented took up about 50 terabytes or so, and this one was quite a bit more than that. So we again post-process our output, interpolate all of our 3D variables to 42 pressure levels, and then horizontally interpolate everything into a 0.14 degree by 0.14 degree lat-long grid. We had a bit more storage for this project, so we are able to save all 6-hourly files. I didn't comb through and pare down any of the output yet, so I'm just waiting for that email to be like, please, we need to save space. But for now, it's safe. And each simulation year takes up about 7 terabytes of space. And the full simulation data set of post-process output, not counting restart files, takes up just over 215 terabytes. We ran these simulations on the Comet supercomputer that was housed at the San Diego Supercomputing Center. Comet has since been decommissioned and replaced with Expanse. And the core hours for this project were sponsored by the Center for Western Weather and Water Extremes out in San Diego, their supercomputing advisory group. With running MPAS on 1,920 processors, each simulation year consumes about 520,000 core hours. So in total, again, including post-processing, this whole data set costs about 15.6 million core hours in total. There was one thing that factored in to the core hour allocation and how many resources that we needed, and that was the time step. So we started out with a time step of 60 seconds. That was 4 times our grid spacing of 15 kilometers. But we did need to reduce it twice during the simulation duration. Once down to 45 seconds before the 2012 simulation, and another time down to 30 seconds before the 2015 simulation. So there's a little bit of numerical instability going on. It was like 1 or 2 grid points all the way up in the stratosphere. So if anyone is working on adaptive time step for MPAS, I would be very, very interested in that capability. Our output here is currently stored on Expanse, and as I mentioned, we do have all 6-hourly post-process output, and we also saved bi-weekly restart files for the same reason as before. If anyone wants to go back and run a certain season, certain events that they want to take a closer look at, then we have the restart files to do so. So getting into the model evaluation, again, we had some key questions to answer. One, again, can this work? Can we run MPAS continuously for 30 years with only 4 sea surface temperatures and get a model climatology that looks like what we expect, at least based on reanalysis? Within those climatological mean fields, since we now have a longer simulation duration of 30 years, can MPAS replicate the variability within those climatological fields? Do we see any biases? Are there any indications of model drift over time? And then, of course, the high impact weather question. What do tropical cyclones look like? What do atmospheric rivers look like? What do MCSs look like? And so on. So I'll focus just here on wintertime patterns of sea level pressure, 500 millibar heights, and 250 winds. And again, we'll just look over the Northern Hemisphere. And then for high impact weather, we did focus mostly on tropical cyclones, but I'll leave that for James to talk about tomorrow afternoon. So the layout for the next few slides will be pretty much the same. We'll have our 30-year ARA5 wintertime climatology here at the top, and then our MPAS climatology here at the bottom. Color shading here is sea level pressure. So really what we're looking for is, can MPAS represent our typical Northern Hemispheric, semi-permanent maritime features? And it is. We have our Aleutian low here in the Bering Sea, our North Pacific subtropical high here off the US West Coast, Icelandic low in the North Atlantic, and Bermuda high in the subtropical North Atlantic. The pattern correlation coefficient between these two plots is very high at 0.98, meaning these climatological sea level pressure patterns shown very much agree with each other between the reanalysis and MPAS. But pattern correlation coefficient only tells us so much. It just tells us if those patterns match. Are we getting the highs in the right place? Are we getting the lows in the right place? It doesn't tell us too much about potential intensity differences. So just at first glance, for example, we can see the Aleutian and Icelandic lows, while they are positioned in the right place, are a bit stronger in MPAS. So this is a bias, of course, in a 30-year average. We didn't expect everything to be perfect. We are at higher resolution. Maybe we're resolving some deeper cyclones, something like that. But we did want to double check and make sure that biases like this are either A, systematic and occurring regularly, or B, dominated by, say, a few rogue years. All that to say is we want to make sure it's not something that's getting worse and worse over the 30-year period. So to do that, we can look at this figure here, shows the average monthly sea level pressure bias over our full 30-year period for the Northern Hemisphere. And thank you to James for making this figure. So to get these values, we took the differences in monthly average sea level pressure from ARA5 and MPAS and averaged those values over the whole Northern Hemisphere. So points here above the horizontal gray line indicate an overall positive bias in MPAS, so a bias towards greater sea level pressures. And then points here below indicate an overall negative bias or a bias towards deeper sea level pressure. And you can see that MPAS is definitely favoring a more consistent negative bias, which makes sense given the plan view that we just saw. We have most of those points falling here below that zero line. The good news, though, is that we're not seeing any evolution in this bias. We're not seeing any growth. We're not seeing any trend in that bias over time, which tells us that our model isn't doing anything crazy like losing mass, which was definitely a reassurance going through this analysis. So next we compared the 30-year climatologies of wintertime 500 millibar heights, again for ARA5 at the top and MPAS on the bottom. Our pattern correlation coefficient here is also high, 0.97. So our climatological wave pattern produced in MPAS does match what we expected to see based on the reanalysis. We are averaging here over 30 years, though, so this is a perfect instance where we were more interested to see how MPAS handled the variability within this climatological field rather than just the mean field itself. So to do that, we did a couple of different things. For one, we used self-organizing maps of ARA5 and MPAS, again, looking at those wintertime geopotential heights. We trained SOMs on ARA5, saved those weights, and then applied those to the MPAS data. So shown here are those results. We have ARA5 on the left and MPAS on the right, and just looking at the 4 primary patterns, again, at 500 millibar heights. And we zoomed in here just on the CONUS for a more local perspective and kind of get that zoomed in view. In the ERA 5 SOM, we do see these 4 distinct patterns, essentially defined by where the upper trough is located and how amplified the overall wave pattern is. About 2,700, little over 2,700 cases or days went into this SOM, and they were just about equally distributed across the 4 nodes. The MPAS SOM shows very similar height patterns across each of the 4 nodes, which is great. We also see a fairly similar distribution across the nodes, albeit with maybe a slightly higher preference for node 3, where we have that ridge right along the US West Coast and that substantial trough over the Northeast and Central US. With the help of Will Chapman, who was previously here at NCAR, we were also able to diagnose leading atmospheric modes of variability in our simulation. So here we have the representation of the NAO, the North Atlantic Oscillation. Leftmost figure is ERA 5, and the middle figure is MPAS. Shading here is geopotential anomaly, with positive values shaded in the warm colors and negative values in the cooler colors. So taking a step back, our high and low patterns in MPAS look very similar to those in ERA 5. But of course, there are always a few differences that we want to point out along the way. For one, the peak of the high here in the North Pacific is shifted a little bit farther west in MPAS. And the strength of the high and low geopotential areas in the North Atlantic are slightly weaker. The bar graph over here shows the bootstrap ERA 5 variance fraction here in the gray outline, and then where MPAS falls within that distribution in the teal line. So not only does the MPAS NAO pattern spatially match what we see in ERA 5, but MPAS is also picking up an appropriate amount of variance in this pattern as well. So we're looking at the same thing here now, but for the PNA, the Pacific North American pattern. Same as before with ERA 5 on the left, MPAS in the middle, and our variance fraction distribution on the right. And shading is, again, geopotential anomaly. So here, our patterns are still pretty similar between MPAS and ERA 5. However, we do see this high center in the North Atlantic is noticeably shifted eastward in MPAS, and the low center in the North Pacific is noticeably stronger. As a result, our variance in the PNA pattern represented by MPAS falls just outside of the ERA 5 distribution, albeit by not too much. And then last year, in terms of our large-scale climatological feature analysis, we evaluated how MPAS represented our jet features using 250 millibar zonal wind. So we can see that MPAS clearly simulated our North Pacific and North Atlantic jets. They look very similar to the jets in ERA 5 in terms of general position and orientation. A couple of differences, of course. For one, the core of the North Atlantic jet is about 10 meters per second or so stronger in MPAS. Second, the core of the North Pacific jet is shifted just a bit farther east, and the jet as a whole appears to be a bit more elongated and extending farther east as well. For example, if we take a look at, say, the 50 meter per second contour and look at that eastward extent, in ERA 5, that contour extends out to about 170 degrees west, whereas the same contour in MPAS extends out to about 160. You could also say that the North Pacific jet maybe has a little bit more curve to it in MPAS, but again, generally speaking, we see a pattern correlation coefficient of 0.99, meaning that these images very much agree with each other. So even with these differences we noted, MPAS still did really well at simulating a present-day climate that's very much representative of what we expected to see, at least based on reanalysis data. We're also relieved to see that whatever biases did exist in these simulations, it wasn't something that was growing in magnitude over time. So in addition to continuing with our TC analysis, again, another plug for James's talk tomorrow afternoon, our next step is to look at atmospheric river climatology, maybe heat waves, MCSs, again, focusing more in on that high impact weather that we're interested in. And in terms of future directions, we're kind of playing around with how best to use this data set. It can, of course, be used as a verification data set or a comparison data set with other similar model simulations across different modeling frameworks. But we're thinking that maybe this could be used as a starting point for different climate change experiments or predictability experiments. So even though the events replicated or represented in the MPAS simulation don't necessarily line up with realistic events, they're still representative of the types of events that we experience. So maybe the output from the simulation data set can be used as a, in very big quotes, perfect control run and be a starting point for climate change experiments. Or perhaps the more unique capability or application could be predictable, practical and intrinsic predictability experiments, where again the output from this data set can be used, again in very big quotes, perfect initial conditions, and we can assess theoretical predictability limits for different types of phenomena over different timescales based on initial condition perturbations, grid spacing, and things like that, which I would of course love to talk to y'all more about as we move into discussion. So just before we close out, I have just a couple other ways, very quickly, that I've used MPAS in the past in case you're curious. So in Michaelis et al. 2021, we ran MPAS experiments of 2 atmospheric river events with associated small-scale perturbation called mesoscale frontal waves. And with the help of Laura Fowler, we removed latent heating to effectively remove that frontal wave and assess how frontal waves, or lack thereof, impacted the storms. The main conclusion was that, perhaps unsurprisingly, in the absence of latent heating and the absence of these mesoscale frontal waves, atmospheric rivers were much less impactful. They were weaker, they were shorter in duration, and they produced less precipitation. In Michaelis et al. 2022, we used MPAS to simulate an atmospheric river event from 2017, the Oroville Dam case, in past, present, and future environments. And then in recent work with my master's student, Hunter Martinez-Buer, we did similar climate change experiments with a sequence of 9 landfalling ARs from December 22 through January 2023. And there are a couple of takeaways here. One was that, yes, in general, atmospheric rivers are becoming warmer, wetter, more intense as we move into the future. But the degree of which that intensification happens did vary slightly based on mid-level temperatures and orientation and things that we're digging a little bit more into. Another takeaway was the recovery time between events. So we saw in this time series here the timing between these colored blocks becoming less and less as we move into the future, indicating that these successive events may be even more impactful with that reduced recovery time. So just some food for thought, again, as we move into discussion. And thank y'all again for being here. No talk is, of course, complete without pet pictures. So shout out to Pickles, shout out to Gravy for their moral support. I'm happy to take any questions and discuss. Thank you so much.
All right, we have time for questions. Just need this so we can throw it around. Questions? Yeah, we'll go with Gretchen first.
Thanks, Allison. This was really exciting to see. Very nice talk.
Thank you.
Yeah, it's hard to pick a question when there's lots of things to investigate here. In your original runs, you obviously picked a range of ENSO conditions. Did you actually investigate anything about the responses in the spectrum of ENSO cases, and was there any good or bad in how well MPAS was performing along that range?
Yeah, we didn't, just because of the sample size was a bit too small. Since we only had 2 or 3 years in each ENSO category, we weren't able to really see a signal, but that would be super curious to investigate. And in the 30-year run, maybe we could look at that a bit more closely. It's a great suggestion. Thank you.
Hi, thank you. And that was a great talk. I had a lot of questions, but I was in particular curious about the daisy chain method that you used. So I think I want to try to understand a little bit more the advantages. So if I understood it correctly, it's basically to reduce the spin-up time, right?
Yeah.
So that you use the model output from the year before to initialize your next year. But then I was curious, because you used this high-resolution SST data, if there's also kind of a spin-up that the model needs to adapt to this suddenly
Yes.
like very inconsistent maybe or different SSTs?
Yeah, absolutely. So we did give every simulation a month of spin up to account for swapping out those sea surface temperatures, and that seemed to be enough. Really, the motivation was not so much for the present day experiments or simulations, but for the future. And so we wanted to do that full year spin up, really get the model in that future climate environment, but we didn't want to do that 10 times. So this was sort of a way that we tried out. It seemed to work okay and helped minimize that time. Great question.
I'll quick jump.
Oh, yeah.
Do the clarification. So there was prediction of the land surface and soil. Is that one of the main things here? Because of course the atmosphere won't have much memory beyond, you know,
Right, yeah,
2 or
we
3
did
weeks. So it's really a
adjust.
surface issue.
Yeah. So we did adjust the soil temperatures, but yes, wanted to make sure those deep soil temperatures retained that warming and didn't have to do that every single time.
Did you look at tropical waves beyond
No.
tropical cyclones? Okay.
Yes, and that is part of James's future work as well, to look at how MPAS
Because
is resolving those
that
waves.
anomalous precipitation of a maritime continent might be related to that, not only to tropical cyclones, but
absolutely. And I've
to wave
talked
activity.
I talked to Rosie, I've talked to Falco a little bit about that too, and so it's definitely on the list for investigation, for sure.
Okay. I think we can toss this one.
Hey, Allison.
Hey, Pat.
Congrats.
Thank
and, yeah, go Pack. I noticed your hurricane tracks kind
Yeah.
of just like disappear once they hit land, except for over India. And I'm wondering, is that just a tracking
Right.
issue or?
Yeah, I think that's a tracking algorithm. When we ran the extra tracking algorithm from Collins Zarzicki for the extratropical transition, we're able to extend those a bit further. But once it stops meeting that criteria, once we don't have a close sea level pressure contour or warm core or anything like that, or start getting super erratic tracks, then the tracking algorithm spits them out.
Okay, cool.
Yeah.
Thanks.
Yeah.
All right, any further questions?
Anything for pickles and gravy?
Any cat questions?
Any questions?
All right, going once, going twice. Okay, well, let's thank Allison once again.
Thank you guys so much.